All right, little update. I was doing some research on Einstein, and everyone knows in 1915 he came up with the general theory of relativity of gravity, how matter is fucking exists in space time, and gravity is actually matter density of matter, and the closer you are to a dense object, the more the gravitational field gets bent around that object of mass, and that's his theory of gravitational relativity, which he developed in 1915. And in 1905, 10 years earlier, he developed E equals mc squared and photon quantum packets of energy. So in 1905, he developed the theory of special relativity, not gravitational. Gravitational relativity was 10 years later. He developed special relativity in 1905 and photons as discrete quantum packets of energy that same year, how they can collide with electrons, which are subatomic particles. Now, always in the world of physics, we are developing the theory of everything. So everybody was fucking discovering bosons and electrons and subatomic particles and nuclear physics all the time. I didn't dig into nuclear physics that much yet. I did a little bit. That'll be the next thing I get into. But first, I got some electromagnetism too. So this is the theory of the history of the world. I'll be using this. I used it for my Egyptian novels a little bit, like camels and horses and that sort of stuff. I don't know. I found it on Amazon. Videos as well. Ancient Egypt. But I'll use this history of the world for a little bit of my creative thinking, historical facts. These two books I bought in university, when I was in university, 2018. And they're James Clerk Maxwell. Look how fucking thick they are. I was studying my favorite course at university, 4th year course, which is also a grad student's course, and the undergrads were getting better marks than the grad students. And I had a fucking 80 or a 90 in that course. And it was called microwave circuits. And it's based on electromagnetism and at high frequencies. Electricity at high frequencies. That goes into microwave circuits for communications, chip design, high frequency signals. And he said he was an electromagnetics professor. And when I mentioned my favorite subject is electromagnetics and how that's what I'm studying, all the other TAs were like, "You're fucking stupid. Everybody hates that shit." And it's true. That was the smallest. The class was so small they had to mix the undergrads with the graduates. So there was like 8 undergrads and 12 graduates, and it was a class of 20. 8 students took that course. And all the other TAs from other disciplines were like, everyone hates electromagnetics. They do analog electronics, they do computer hardware, they do, they do control systems, they do circuits, they do energy and distributed generation. They do electric machines, electric motors, Verilog, analog, digital circuits, communication systems. Nobody does electromagnetics, but to me, that's my fucking favorite shit. So, in the class, the professor said, James Clerk Maxwell wrote these 2 fucking books on electricity and magnetism. And if you have a chance, go out and buy it. Everyone was fucking sleeping in that class. I went out and I bought these books. And I tried reading them. Now, it's difficult to understand because, first of all, they were written in what fucking year, bro? $30 for the book. When were they first written? 1891. This edition was first published in 1954, but the original 3rd edition was published in here's my bookmark. The original 3rd edition was published in 1890, which means the 1st edition was probably published 1880. So 1800s, before they even fucking had electricity, before Nikola Tesla. It was James Clerk Maxwell. And he discovered not only light, but electromagnetism and his Maxwell's equations, which are highly, highly principled and mathematical. That's the second reason I never understood the fucking books and gave up reading them. Because they were so technical. I was already learning this shit as a 4th-year student at a top university in the world. Not in Canada, in the world. Top university in the world. I'm trying to study this shit as a 4th-year student after 10 years of undergrad. And then I bought the fucking books. And I'm good at it. I got 90 in the course. Still can't understand this shit. I don't even think the professor understood this shit. Maybe they did. When they teach us Maxwell's equations, I have an easier time understanding Einstein than Maxwell. But Einstein understood Maxwell. All of Einstein's work on E equals mc squared came from fucking Maxwell's laws, because they discovered the laws of electromagnetism. So, what Einstein did was, when he was a teenager, I don't know how the fuck he was studying this. They were geniuses a long time ago. When he was a teenager, he said, what if you were traveling at the speed of light and following a beam of light? But you were traveling at the speed of light. Wouldn't that mean light stands still? But Maxwell, by his principles, for light to exist, it must always be in motion. Which led to Einstein's theory of relativity, frames of reference, and he started working with this. He said, well, if light must always be in motion, and my frame of reference is at the speed of light, then light would stand still in my frame of reference. But light must always be in motion. So that's how we concluded that light must always be traveling at the speed of light, no matter your frame of reference. So no matter how fast you are traveling, light must always be traveling at the speed of light. And therefore, you can never travel over the speed of light, because that would be impossible. Then you'd beat light. That's not possible. Light must always be traveling to exist. And that's when they discovered light was he discovered light was quantum packets of energy called photons, instead of like a beam or a wave or something. You know, it is a beam and a wave, but as discrete photons. And then he did some mathematical examples, which I worked out by myself because I've seen the solution before, but I just discovered it myself. Case of relativity. Basically, you have your classical physics. Velocity equals meters a second, right? So distance over time. So velocity equals distance over time. Time equals distance over velocity. And distance equals velocity times time. That's your classical kinematics. That's common sense, bro. That's Newton's physics. That means Newton was alive even earlier? Who knows? Probably Newton was alive earlier. So that's your Newtonian physics. And if you draw frames of reference, right? If you have an object, but it's moving very quickly. And you have a laser. What is a laser? A laser is a source of light. A laser is a source of light. And all that laser is going to do is shoot a beam onto the roof of the object, into its spaceship or whatever, and back down into a detector, straight in a line. So for the object, it's carrying the laser and the mirror, and it's going to measure, because light doesn't jump, it still has to travel just very quickly. So how long does it take for this beam of laser to bounce off the reflector and catch it in the detector? Well, for the person carrying that laser, no matter how fast you drive or fly or whatever, it's always going to be the speed of light times the relative to the distance between the reflector and the mirror. Straight up and down. All right? Now, that's your frame of reference, and you are traveling at the speed of light. You're traveling at some fast distance. To an observer who is looking at you, but is not moving at your speed, right? This is what you see, this little up and down. He sees this. He sees you going this way. So your laser and everything in your that you're carrying in your spaceship, he sees it moving, all of it moving. He sees all of you moving. Nothing standing still, all of it moving. So that includes the laser. So the laser he sees as going in a triangular pattern, because you see it going up and down. But when you're moving to a guy watching you standing still, he sees lasers going like this and like this in a triangle. So we can cut that triangle in half, and then got two right angled triangles. And because you're not accelerating, you're moving at a constant velocity, those two right angled triangles are equal. So it makes it simpler. Which is why we have the right angled triangle in the first place, kind of, whatever. So he sees this triangle, right? Okay, fine. Now here's the catch. You see the beam of light going up and down. He sees the beam of light going in a triangle. Therefore, like the time that you take to catch the laser and the time that he takes to catch the laser would be equal if the speed of light changed with how fast you were traveling. Maybe the speed of light to him also looks faster because you're traveling fast. That's not true. The speed of light does not look faster with that triangle. The speed of light is the same in every reference. So, this little shooting up and down, and this little triangle that the observer sees, there's different distance between going up and down and going in a triangle, different distance covered, but the speed that laser is traveling at to cover those different distances is the same. C, the speed of light, 3 times 10 to the 8 meters a second squared. Meters a second, not squared, meters a second. So, this little guy is going in a small distance, And this guy's going a longer distance, but at the same speed. Therefore, if you calculate time based on distance and velocity, and this time based on distance and velocity, who has a bigger time? This time 1 is short distance over c, and this time 2 is bigger distance over c, because it's a triangle. It's not just up and down. And mainly, it is these two diagonals. Here, the light is going up and down, and here the light is going diagonal, diagonal. Diagonal, diagonal is longer than up and down. So this distance, but the velocity is the same, c, speed of light. So this time is this long distance over speed of light. And this is short distance over speed of light. So this time, because it's shorter distance, this time is shorter. And this time is longer, because the speed of light is the same in both frames of reference. So the guy driving, and it's point A to point B. By the time the light starts is point A, and when the light bounces off the mirror and hits the detector, that's point B. So the event is driving point A to point B. The driving stops by the time the light hits the detector. So driving point A to point B, this guy sees a shorter time than this guy sees you driving point A to point B. This guy watches you driving point A to point B, longer time. How much longer? Depending on the speed this guy is traveling. Depending on the speed this guy is traveling. So you're traveling at a speed, right? You will go D1, T1, T0. I call it T0. And this guy, T2, will be a factor of how fast you're traveling. Not just for the laser, though. That's what's interesting. This little laser shooting off the mirror is just one of the laws of physics. This difference in time, based off frames of reference, who's traveling faster, is interconnected by the speed of light. And that means this guy sees different times from this guy based on how fast two people are traveling to each other. Maybe this guy was traveling in the opposite direction, and this guy was traveling in this direction. 3D space. They will see different times. Not only that, but time is related to distance and speed. So speed is the factor we are isolating. So you will see different times, and you will see different distances. You will see different distances. I haven't worked out how you would see different distances, but distance and time are related. And speed. Now, speed is the speed of light and your individual speeds. I don't know if speed is dilated. I don't know if there's such thing as speed dilation. Let me Google that right now. Google that right now. So time is different. Time passes, but I don't know how does speed work. I don't think there's speed dilation. I know there's distance though. All right, so this is a very interesting factor. Now we know that time, based on the speed of light in the universe, speed of light exists. In order for the speed of light and Maxwell's equations and light to exist in always in motion at the speed of light in every frame of reference, nothing could catch it, nothing could push it, nothing could slow it down, speed it up. Time must be relative. Time must be relative for your frame of reference. That includes biological processes and decay and time of the galaxy. So, if the people in the rocket ship age 1 year, the observer will age much longer. The observer can age 7 years, like in the movie Inception. Not Inception, what's that movie with Matthew McConaughey? Interstellar. He aged 1 hour and they aged 14 years on Earth. 7 years on Earth. He aged 1 hour, they aged 17. Took him 2 hours to fix the portal. His daughter aged 14 years. That's the whole point of the movie. But I didn't see it. But I heard about it. So we know time dilation exists based on your frame of reference and how speed you're traveling. Now there's also distance dilation because I know it proved it. Now we're isolating for the variable speed, which is the speed of light. Distance dilation, it says, is for the person moving faster, the distance he has to cover is shorter compared to the stationary person. So let me figure this out. Let me just figure this out. There's distance, and basically that's his theory of relativity, is that he took these frames of reference and the speed of light and concluded that the laws of physics, which is the speed of light, must be constant, and nothing could push it or change it or go faster than it, based on Maxwell's equations. That there's time dilation, not just the laser, but all of time, and which leads to distance dilation. Let me just type in distance dilation formula, and I'll fucking know what it is. So it is L. I was going to call it L contracted. It should be L2, but I'll call it L contracted equals L naught proper length times the square root of 1 minus v squared over c squared. So because it's a square root of 1 minus something, you're traveling at the square root, which is you are really fucking contracting this distance. However, the square root is nullified because the second term in that square root that you're subtracting from 1 has the denominator of light squared. So it's your speed squared over the speed of light squared. Okay, so if the observer sees, say, 1 kilometer, but you're traveling very fast, not only are you fucking traveling faster, but you're probably traveling like 400 meters at that faster pace as well. So there's distance dilation. So if I see 1 light year and you are traveling at 80% the speed of light, you don't see 1 light year. In fact, you see, I'll tell you how much you see. So if you're traveling at, instead of seeing 1 light year, 80% of c, that is 0.8 over 1. Minus 0.64. Wow. 36 squared. If you're traveling at the 80% the speed of light, you're traveling 60% of a light year. So if you're traveling fucking, oh, then there's a square root of that. Fuck you. Yeah, that's what I did. So if you're traveling, if I'm just chilling and I see like 1 light year in between galaxies, but you're traveling at 80% the speed of light, first of all, you're traveling at 80% the speed of light. Second of all, you're going to snap by it because you're only traveling 60% of that distance. You're literally traveling a shorter distance. So now we know that time is different depending on how fast you're traveling. Now, once again, the variable we're isolating for is your speed. How fast you're traveling relative to everybody else. So, how fast you're traveling relative to everybody else is going to change how fast everybody has time, experiencing time, and how much distance everyone else is experiencing. This shit will get very fucking interesting in quantum physics, quantum mechanics. Because electrons travel at the speed of light. That's why they're related to an electromagnetic wave, which is light as well. So light and electrons are electromagnetic waves, which travel at the speed of light. But when you put electricity into a conductor, it doesn't always travel at the speed of light. The materials are imperfect. I guess the electron bounces around at the speed of light, but the flow of current doesn't travel at the speed of light. Close to it, but not that close. But the current, which is all the electrons, they're going bouncing all over the place across impurities in the metal. And that changes how fast the current will travel. But there's got to be other properties of metal with conduction or other subatomic particles like reactions and things that fire off from there that will have fucked up times and distances compared to humans and stationary observers. Because the theory is Maxwell's theory that nothing travels speed of light is constant and every frame of reference must always be moving in motion. So, what next we will investigate is Maxwell's equations, the books. I got part 1 and part 2. We will investigate nature of electromagnetic waves and particles such as electrons and quantum interactions. Nuclear physics. That's what we'll look at next. And then we will look at how we can tie that into electromagnetism. So I got my little notebook where I got my Maxwell's equations. I started off with, this is the theory of that Einstein when he was a teenager. He said, can anything travel like the speed of light? And then his frames of reference, and then his mathematics leading to time dilation and distance dilation. And I started that off with my own little experiment based on a Google search that time is moving speed of light at the speed of light equal in every frame of reference. And I did my calculation there. So I'm going to upload photos of this. And here's where I started my book on oil, Einstein, and physics. Because I wanted to know more about the molten core of the Earth and the physics of electromagnetism and nuclear physics. And Einstein worked on all of that plus gravity. And then I started off this little page with Einstein's rough work. So I'll just write down rough work. All right. That is rough work. So going forward, I'm going to study these on the very home page. This stuff. I'm going to title this book EM. That's my little book, Nick EM. And I started making this research based on my book Crystal Vortex Galaxy, which is, I like to do all my major literature, fantasy and fiction, with some historical or scientific facts to make it more believable and realistic. So I did ancient Egypt, I did Rome, you can do Greece, you can do World War I, World War II, you can do the Renaissance, 1400s Italy, you can do the medieval ages, you can do the India and then China and Japan and the spice trades, Christopher Columbus, Africa, Attila the Hun, the Mongolians, and China, and the Native Americans. And it all started from Egypt and the Romans and the Greeks. Egypt, Greek, Roman, Indian, Chinese, Japanese, Hindu, which is the oldest religion, as long as Egypt, 5,000 years around the time of Egypt. So you got all that. Confucianism is China. And then Romans did Christianity. All right, so that concludes this little video of Einstein's quantum mechanics. This will be titled Einstein's quantum mechanics. And part 2 will be my quantum electromagnetics. All right.